I get that too? Yeah. Sir. Do you want this?
Put it right here.
Please, can you give me the paper? I want to see what we get. Yeah, I don't care if there's a video of what you can see.
Attention students, class begins in 1 minute. Please transition quickly to class.
No, it's today. She just said it was in Thursday. So the count slide need to be written. Wow. What's up? You got everybody working for school. I'm the manager. Nah, wait. I'm only doing that shit for practice. Practice time, take this from my shit. So breaking the page blockers. I'm writing these and it's putting on the plate.
Okay, everyone, when the bell rings, I expect you to be seated on your designated seat and start working on the do now, which I mentioned there. Okay? Exarian, please listen to me what I'm saying. Okay? So before the bell rings, everyone should be seated and start getting ready to work. So now I want you to take out the handout from last time, or you will do day 4 and complete the independent practice. And you have around 7 minutes to do that. Say again. So what are we doing over the next 7 minutes? Doing the independent practice from last time. Yes. You don't have it from last time? Yesterday was it?
Oh, so you only work on that on the weekends or
Try to do it. Okay, I'll call out your names for attendance. Jacqueline, Cedric, Darian, Jamarion, Jamar, George, Miriam. Say again? For today is here. But you need to work on the menu from yesterday right now. You don't have it? No, I lost it.
I don't have, what they do, when we play, I'm gonna, they use it on the gym.
There you go.
Come on. Oh, yeah, something. If you play, I'm not on my man.
Kenneth, Christina, Janet, Jesus, Isaiah, Jacob, Cyrus, Victor, Nathan, Diana, Anthony,
Here.
Gregorio, Xavier. Alright, thank you very much. Any question from last class? Okay, now I'll start off with today's lesson. So, let's do this problem now. This is page two or page. Okay. So the first page is pretty much from the last time. This is the page we are on. The last handout there was an exit ticket, but we are not doing that, so I'm not discussing that exit ticket right now. But here it says consider the function that models motion of Ferris wheel. So we are given a function, and when you look at this function, you immediately should have the general form of the function for comparison. So what is the general form of your function? A. Can someone tell me? A sine W X very good. Okay. So you must always have this thing in mind, and now that we have seen it quite a few times in almost every handout, we have this equation. Particularly the first 2 days of this module, this equation was on the first page, and all these symbols were clearly explained what they represent. A is the amplitude, W is the what is used to find out the period and frequency, H is the phase shift, and K is the, okay, Darren, can you please move here? Oh, alright, thank you. And K is the midline, okay? So, now, we see this and we are going to answer these questions. How would this formula change for a wheel with a different diameter? So if the diameter of the wheel is changed, how this formula will change? It says how this formula, which is here, change for a Ferris wheel with a different diameter. So let's say now I draw Ferris wheel, okay, and then we have this sine function, and we have this here, we have this here, we have this. In relation to a Ferris wheel, what do each of these represent? Or even this here. So 25 reflects the amplitude, right? And 40 reflects the midline. So in case of a Ferris wheel, the midline is basically where your graph would be. So it's basically the initial height. Is it like zero height or is it some positive number? Okay. So when you board on the car on a Ferris wheel, you need to go high a certain amount and then get boarded, or you just board from immediately. Okay? So this is now we are having this was good, answer was right, but for the general function, midline, amplitude, phase shift, and all that. But now we have to answer this question in terms of the Ferris wheel. So this 40 is the height of your platform, like a minimum. Maybe it's this height, maybe it's this height. Okay? So we don't know. This has to do with the diameter of your fence. Okay, remember we had like going up plus and going down negative and so on. This is the period. So period and frequency, they are both inverse of each other and they both depend on W, right? So this is W here, right? So the rate at which this wheel rotates, how much time it takes to complete one rotation, that is here. And then this is the starting position. Where do you start it from? Did you start from here? Did you start from here? Did you start from here? So now, when you answer this question,
You said what is the starting position?
what is what?
You said what is the starting thing? What you say?
The starting thing is this point here, like 1/8.
Alright.
Basically, if there is nothing here, and we take the standard starting position, we can say, okay, start from here. Okay? So, whatever, if it changes, then that number will change. Okay? So, the first answer, it says that 25 would change the radius of the fence. So, this 25, the amplitude, if the radius of the fence changes, then this number will change. Okay? How would this formula change for a wheel at a different height of the ground? So this height, if that height changes, how this formula will change? What do you guys think? So think of your function, okay? And whatever is the shape, and for simplicity, we assume that, let me do it here. This is the shape of my function. Okay? Now, if the diameter of the wheel changes, the amplitude changes. So, what will happen? It will go like this. If the diameter is high.
Attention teachers, please pause to take attendance.
And if the diameter drops, becomes less, it's again less. Nothing else is changing except for the amplitude. If the distance of the ground changes, then this entire graph will be lifted. The same shape for the first one, but it moves up or down depending on this height, this k. So the second part which says how would this formula change at a different height of the ground, you will say that this number will change. Okay? So this is where we are connecting maths with real world. Okay? Alright? Everyone understands this? So this is the function that represents the motion of a car in a Ferris wheel. In the first question it said if the wheel had a different diameter, how will the function change? And we said the amplitude of the function will change because the amplitude of this function represents the diameter of the fence. In the second question it asked how would this function change if the wheel was at a different height of the ground. So for this is the height. Okay? So this height we are looking at, and if it changes, so in this function that height is 40. So if the height of the wheel of the ground changes, it becomes less, let's say 20, or it goes further higher, 50, then this number will change. Okay? So keep making a note of it on your handout so that you know what we are talking. The 40 would change to the measurement from the ground to the central axis of the Ferris wheel. So this 40 is basically central axis of the Ferris wheel is here. So this distance is, because we are considering from here. So the 40 will change. And then the next is, how would this formula change for a wheel that has a different rate of revolution? So that if your wheel is rotating at a different speed, and what will change in your function? Yeah, so if that changes, like earlier, let's say it would complete one turn in 5 minutes. Then you change it so that it completes one turn in 8 minutes, for example, or one turn in 4 minutes. You change the time it takes to complete one rotation. What in the function will change? Yes. Close enough. T is my time for the variable, so this is the input variable. But this 4 pi is W, right? And W gives me the value of my period of my function, or frequency of my function, right? So that comes from how it is, how fast or slow it is moving. Okay? So if we had a different rate of revolution, then in our function 2 pi should change. The number of revolutions per minute would change, so the period and frequency would change. So that means we'll have something else instead of what we had before P. And then the last question is, how would this formula change if we model the height of a passenger car above the ground from a different starting position on the Ferris wheel? So this question is pretty long, so we can break it down. Height of a passenger car above the ground. So far we always have this car, and then we calculate the height at different positions, right? This question says we don't have this as a starting position. Instead, we say that let's start off from here, for example, or let's start off from here. So this is not the starting position. This is the starting position, or this is the starting position. If we change the starting position of our car on a Ferris wheel, how will the function change? What do you guys think? So let's go back to the function. This changes if the diameter of the wheel. This changes if the height of the wheel of the ground changes. This changes if the rate of rotation changes. So what we are left with? This, right? This is the phase shift. Remember, phase shift is basically if you have a graph like this, and you just move this graph to the right or to the left. So you make it like this. Okay? So this is basically the phase shift. If the phase shift changes, that means in this particular case, for example, or if you go further and complete it in the beginning, you're like here. Okay? So at 0, your height was 0. At 0, your height is negative, right? So basically you say that maybe this is your starting position. So from here to here, it's a negative number. Okay? So if that happens in your function, that shows over here. Okay? So this is the fourth and the last thing that we notice. So it says the height of the time corresponding to t equals 0 would change. So changing the phase shift could horizontally translate the function. Translate means shift the function to the right or to the left to have the correct height correspond to the starting time. Okay? So we had an example of the Ferris wheel. From the Ferris wheel, we pick one particular car at a specific starting position, and then for all the angles, we noted down the height of a person with respect to the center of the Ferris wheel, and then we graphed that, and then we came up with an equation, with a function for that. Now we see that how each thing, different information affects the function. Any questions so far? Yes, German.
What does the D and the H represent?
H is your output. H is the height of the person with respect to the point. So the center, if we are taking the center as the reference point, then its height with respect to that center point. Up is positive, down is negative. Okay? And then T is, instead of angle this time, we are taking the time of rotation as the variable, input variable. So at T is equal to 0 means when he started off. At T is equal to 10 seconds, after 10 seconds where he will be. So if it completes complete rotation in 60 seconds, for example, 1 minute, then after 15 seconds, it's gonna be a quarter of the rotation. You know, after 30 seconds, half of the rotation. After 60 seconds, complete rotation. So T is your input variable. Very good question actually. Because so far, we always had either X here, or we could use the symbol theta, and in both cases, this was the angle in radians. This time, they take T, which is time, okay? So, yes, this was a good question. And then always, H is your Y, basically, the output variable. And in parentheses, if you write T, it means H as a function of T. Height as a function of time. Okay? So anytime we name a function, we use some letters and then we say it is a function of whatever variable it is. So let's go to the second example. And it says, we have a windmill example now, which is 20 feet off the ground. The center of the windmill is 20 feet off the ground. Sails are 15 feet long. And then this guy, Don, is caught up on the tip of one of the sails. The sails are turning at a rate of 1 counterclockwise rotation every 60 seconds. So this is the picture. Okay? This is a windmill. This is 15. The guy is here. And then the overall height of the center from the ground is 20 feet. Say it. It's coming from a story actually. The book is titled after the name of this guy, Don Quixote. So I don't know if you call it Quixote or Quixote. So this is he had a fight with the windmill in that storybook. So I skipped the first paragraph, which was introduction to the book, and I just went directly to the relevant portion. So now, if we start annotating 20 feet off the ground, sails are 15 feet long. Okay, he is on the tip of one of the sails, and the sails are turning at a rate of 60 seconds, and the movement is counterclockwise. Explain why a sinusoidal function would be used to model his height above the ground as a function of time. So now, although this is a windmill, it's not a Ferris wheel anymore, it is still moving in circular motion. It is at a certain height, right? So if he is stuck here, let's say, this is his starting position, then and it goes with a certain rate, 60 seconds. So we can model it like 90, 180, 270. So it's 15 seconds, 30 seconds, 45 seconds, and then 60 seconds. And 0 seconds. So always, just like a Ferris wheel, we can have his height off the ground at different times. So once it's complete rotation, it will start off again the same way. So we can definitely model this as a sinusoidal function, which is a sine or cosine function. Okay? It says since he is moving around a circle, the sine function measures vertical displacement of an object moving around a circle. We can use a sine function to track his position above and below the horizontal line to the center of the sails. So this is the horizontal line, and this is to the center of the sails. So we can do that, and this is the reason we can do it. Okay? Then the second part says sketch a graph of his height above the ground as a function of time. So assume t is equal to 0 is the time when he was closest to the ground. So now, not these, because this was just to give you an example, but we are taking time right from here. So we can write here t is equal to 0. This is 15, this is 15, and this is 5. Okay, because it says 20 feet from the center to the ground. So when he is here, now I will start making a table. So I will have time, and then I will have height. So time, height. When time is 0, it just started off. What is his height off the ground? Isaiah, tell me. He is here. What is his height off the ground?
Said what, sir? Say the height? I got you.
Can you say something? It's 5.
The height is 5?
Yeah, from here to here, the height is 5.
How do you get 5?
Because from here to here it is 20, and from here to here it's 15. So if you look at this diagram,
Okay, I got you.
it says the height from the center to the ground is 20, and the height of the length of one sail is 15. So 20 negative 15 is 5. Yeah. So at time 0 its height is 5. After let's say 15 seconds, what is his height? So in 15 seconds he should be here. So again, 0, remember if we consider this point, then it will be 0, definitely. But now we are considering from this point. How high he is from the ground level? 25 plus 15. So the height is 20. Then if you increase the time to 30 seconds, what's the height? Oh, 35. Good. So 35 for 30 seconds. 45 seconds. What's the height? Yes, you come back here. So 15 plus 5 is 20. And then 60 seconds. What's the height? Second 5. Perfect. So now when you graph it, you will have, this is going to be 5 at 0, and then after 15 seconds it's going to be 20, then after 30 seconds it's going to be 35, right? And then 45 seconds is going to be again 20, and then 60 seconds it's going to be back to 5. So this is how your graph will look like. Okay? So you notice that anytime there is a circular motion, things are pretty much the same. You have a reference point from which you measure your height up or down. The reference point may change, the starting position may change, the diameter of motion, it's circular motion, the diameter may change. Okay? So any of these things will change the graph of your function. So now this here, since we had an initial height of 5 feet, we always are 5 feet above. 5 feet above. 5 feet above. So my entire graph is shifted up by 5 feet. What is the midline in this case? The midline is basically you add the maximum point and the minimum point and you divide by 2. So 35 plus 5 over 2, 40 over 2 is 20. So the midline is at 20 feet. Okay? Alright. So here it says the amplitude is 15 feet, which is coming from here. The period is 2 pi by 60, that means 60 seconds. Okay? So 2 pi by 60 means one complete rotation in 60 seconds, which is the same as pi over 30. So 2 and 60 simplify to 1 over 30. Midline has an equation y equals 20. I just did it in front of you, right? So this is the information we get and we use that for our function. So if you need to come up with a function, the equation of the function, this is how it's gonna look like. 15, the amplitude, 20 is the height of the center of the ground. Okay? Then pi by 30 is the period, the rate at which it is rotating, and negative 15, you start, instead of starting from here, you started off from here. So you shifted your graph backward by 15 seconds. So this is that is why you are having negative 15. Okay? So now I don't want to show you the answer to the next part, but let's look at the question. After 1 minute and 40 seconds, Don fell off the sail and straight down to the ground. How far did he fall? Yes? No. If you don't mind, just stay on, because we are going to have an assessment when we are near the end of the class. So please, thank you. So here, now we have the function, and we need to find this statement, this question simply says, what is your age when t is 100 seconds? After 100 seconds, when he falls, from what height did he fall? Okay? So now, all you need to do is replace this t with 100. Okay? And when you do that, you will have 15 sine of pi by 30. 100 negative 15 is 85. So pi by 30 multiplied by 85. And then let's leave this and this aside for a while. So sine of this. Then you let's say we want to simplify it further, so we divide by 5. 5 times 6 is 30, and 5 1s are 5, 3 and 5 35, 5 7s are 35. So now it is sine of 17 pi by 6. 17 is bigger than 6, right? And if we think in terms of multiples of 6, it's bigger than 12, it's times 2 is 12, it's less than 18. So we can write this as 12 pi over 6 plus 5 pi over 6. Okay? So 12 pi over 6 means 2 pi. 2 pi means one complete rotation. So that doesn't make any difference. So we come down to sine of 5 pi over 6. Pi by 6 is 30, and 30 times 5 is 150. So it's 150 degrees. Sine of 150 degrees is the reference angle will be 180 negative 150, 30 degrees. Sine of 30 is 1 over 2, excellent. And it's positive. So this is just 1 over 2. This complete thing simplifies to 1 over 2. Once again, I know there are many steps involved. I replace t with 100. 100 negative 15 is 85. Please, everyone stay up. Nod your head down. Marion, Anthony, George. Guys, can you move them a little bit? Can you shake them? There.
I miss you, man.
So what did we do? T is 100 seconds.
What?
Yes.
What do you do with the 50 and 75?
This one? Yeah. This and this are still there. I just focus on this part to simplify. So I'm gonna go back and take those into account as well. 100 negative 15 is 85. 85 times pi by 30 is simplified to 17 pi by 6. 17 pi by 6 is the same as 12 pi by 6 plus 5 pi by 6. So 12 pi by 6 is 2 pi. 2 pi means complete rotation. You can exclude that. Sine of 5 pi by 6 is the same as sine of 150 degrees. Gives you a reference angle of 30 degrees. So sine of 30 degrees is 1/2. So once you have 1/2 here, 15 times 1/2 plus 40. So that is 47.5. Okay? So this is going to be the answer. So 15 over 2 is 7.5 plus. Oh wait, this was 20 actually. Sorry, not 40. So this is 20. So 27.5. So these are the steps on here. 100 negative 15, 85, and then you change that to this, and then you solve it. Yes.
What's the answer for 5 over 7 is 8.4 seconds?
What's the answer?
5 over 6, is that what's the answer? Is it 400 seconds?
No, the answer is 27.5 feet. It's the height. Answer will be in height. He fell off from 27.5 feet. Yeah. After 40 seconds, he held on to the same for 100 seconds. So he completed one rotation in 60 seconds, and then in the next 40 seconds, and eventually he fell. So when he fell off from a height of 27.5 seconds. Okay. So does this class end?
Yeah.
9:35? 9:30. I'll give you the assessment now. So do the independent practice later on and bring it to the class next time. We can plan some activity on Friday if you guys want. So you have around 12 minutes to do it. So you bubble this Cantron. George.
Further, for Jorge Mancillas is in the front for pickup. Mancinas. Thank you.
You're always taking your height from this point. Just read it. It will tell you where your height is. So this like we have formula. So from here, what is the altitude? What is the midline? What is the period of the formula? So you just write a formula. Yeah. They gave it, but you now have the graph, right? So we need some practice when we look at the graph. We try to see how we can get different parts of our function, the amplitude, the midline, the period of our function, right? So you do the same thing and try to write formula. So first of all, what are you going to find out? Like that? Now, what are these that you're finding out? The height is your output area, right? You're there. Good. It's like that. Yes. I'll be with you just. It says clockwise or counterclockwise? It doesn't say anything. Here it is. Let's see. What are we doing? You can take counterclockwise. Okay. So what's your question? Yeah. Yes.
like I marked down important information in the statement, do the same way, annotate your problem. So you will know what is your starting position, what is the reference point, and all those kind of things. To graph the function as part A of problem 3, try to make a table. So for different times, where will be your height? Just like I made a table, and then take those points from the table and put on the graph and connect these points. You guys need more time? How many of you need more time? Please raise your hands. Okay, I'll give you 3 extra minutes. So, you finished 10? Try to work on the penetration problem. It's gonna like. Just write your name on the front paper as well. Question.
this one?
Oh, I was being recorded. It's crazy.
Okay, please turn in your papers before you leave.